Good morning. This is Mark Richardson. I am speaking to you this morning from Centennial, Colorado. It's a cloudy morning and looks like we're going to have some snow here today. Anyway, this is our monthly time together. We're going to spend an hour together and we're going to talk about structural dynamics modification, which is one of the features in ME-Scope, one of the more advanced features. We're going to go through using a very simple project, one that most of you who own ME-Scope are probably familiar with, called the Jim Beam. And we're going to look at the mode shapes of the Jim Beam and how we get them from experimental data. We'll curve fit some FRFs, and then we'll talk about scaling the mode shapes to obtain what we call a modal model. So the whole idea is that we can obtain a set of mode shapes from experiment or from analysis, FEA analysis, and use those mode shapes as a representation of the dynamics of the unmodified structure. Then the SDM algorithm uses those mode shapes together with modifications to the structure. And with the Jim Beam, we're just going to attach some springs to it and look at how those spring stiffeners modify the modes of the structure. So SDM starts out with a set of modes called a modal model. It then uses some definition of the modification. In this case, we're going to put some springs on a model. We can do more sophisticated plate elements, solid elements, substructuring, tune absorbers. We can do a lot of different things with SDM. But today we're going to go through some simple examples, and then we're going to also look at something called modal sensitivity, which kind of works the problem in reverse. What it does is ask the question, how much stiffness, in this case, do I need in the spring modifications that I add to the structure? How much modification do I need in order to move certain modes to different frequencies? So the whole idea of SDM is to modify the structure physically and then calculate the new modes, the modes of the structure with the physical change to it. And we'll see that this algorithm is very fast. Now I can do the same thing if I have an FEA model and I go back and change some of the properties of the finite elements in the model. Then I can recalculate the new modes of the model. So FEA is certainly useful for doing the same thing. However, typical FEA calculations are much slower than the SDM calculation. FEA works in the physical dimensions of the model. And so if I have many degrees of freedom in my mode shapes, or in the model itself, many points and the directions associated with each point, then I will have to solve for the new modes in the physical space. SDM solves for the new modes in modal space. So it solves a much smaller problem, but again, the underlying assumption is that the modes represent the majority of the dynamics. Now we know that in the real world, everything has modes of vibration, and we like to say that the modes exist between DC and daylight. In other words, there's many modes in structures. However, for most practical work, the lowest frequency modes, the ones that are closest to DC, are the ones that dominate the response of the structure. Typically, if a mode is getting excited, if a resonance is getting excited in a machine or in a structure base or a building or a bridge, whatever. It's the low frequencies that dominate the response. And so those are the ones that we need to include in our modal model in order to obtain an accurate description of the dynamics. Okay, that's enough of the preamble. Let's open up this project. And so we've got several models here, and we're going to use these different models. This is a model of the gym beam. It's as you can see, there's three aluminum plates, and they're attached together with cap screws. There's 3 on the top and 3 on the bottom. So very simple geometry, but even with a simple structure like this, the mode shapes can be rather unpredictable. We'll have torsion and bending modes as we go up in frequency. So we'll look at those in a minute. Over here is an FEA model that simply has plate elements in it, and we'll compare its mode shapes to the experimental mode shapes that we obtained by impacting the gym beam. Now let me put some points up here so we'll just get familiar. These are the test points on the gym beam, and the way the data was taken was with an impact hammer applied at point 15 in the vertical direction, the Z direction. So point 15 is out here on the end of the beam structure, the upper plate. That's a very sensitive point, so that is called our reference, and we want to choose a reference that's active, where many of the modes are going to be excited when I hit the beam structure with an impact hammer. The impact hammer, of course, will put a wide band of frequencies, excitation frequency, into the structure, and the whole idea there is to excite many of the modes simultaneously. And then we use curve fitting to extract the modal parameters of each of the modes from a set of measurements. So then, in order to take the data here, we roved a triaxial accelerometer to all of the 33 points on the model. So you can see that there's 15 on the top plate, 15 on the bottom plate, and then on this vertical plate here, the back plate, there were 3 more measurements taken. So the model was set up, the orientation of the accelerometer at each point had to be included in the model so that when we do animation, we get motion in the correct directions. Now over here on the FEA model, we're going to use the FEA data to do some scaling, just to look at what it means to scale mode shapes and what unit modal mass scaling is all about. That is the way in ME-scope that we preserve the inertia and stiffness properties of the structure. So over here, if I click on this model and I turn on its point labels, you can see that it's got many more points in it, and that's typically what we want to do with an FEA model. Not a lot of points, but a few extra points here, so that we get some mode shapes that will match up with our experimental mode shapes. But you can see the important thing here, and one advantage of doing this inside of ME-scope itself, is that I have common point numbers between the experimental points, the test points on the experimental model, and the same geometric locations on the FEA plate model. So you can see here I've got point number 1, 2, 3, 4, and 5. Let me see if I can make those a little bit clearer by labels. I'm going to take off the transparency so the labels are a little clearer. Let me do the same thing over here. I'm in here under the labels, and here it says transparent background. We don't want transparent. Now the labels show up a lot better on both models. We can see over here that point 1, 2, 3, 4, and 5 are geometrically the same as points 1 through 5 over here, and so forth. And then the FEA solver and MeScope will number the other points so that we can animate shapes on this model once we have calculated them using the FEA capability. Let's go back and look at the data that we obtained here. So I'm going to open up a data block, and here's one called FRFs. So this is the measurements, and I'll make this large. And I'm going to go into curve fitting. So we've changed some of the terminology here. Curve fitting is a way of, we used to call this modal parameter estimation, mode shape extraction. These names all refer to the same thing. So I'm going to go in here to curve fitting, and the whole idea of curve fitting is to match an analytical model of the FRS to the experimental data. And in the process, we obtain a set of modal data over here, frequency, damping, and what we call a residue, which is the magnitude and phase of, or let's say the participation. We can think of the magnitude as the participation of each mode in each measurement. I'll take you through the curve fitting. This kind of data is what I call textbook data. I just cleared out all the curve fitting that was part of this data block, and you can see that I've got 99, let me open this up here, I've got 99 measurements in here. They're numbered M pound 1 through 99, and let's get down to curve fitting. I'll just make this a little larger so we can see everything. I'm going to hold down the control key and spin the mouse wheel here, and now you can see the data that's in this data block a little more clearly. There's measurement 99. So if you look at the DOFs of each of these measurements, the reference follows the colon, and that's minus 15Z. That's where the impact hammer was applied. And then the roving, here for 0.1, we can see it's 1 in the X, 1 in the Y, 1 in the Z. So we've defined all this data, and we use an accelerometer and a load cell for the force. So the units of these FRFs are G's per pound. Okay, so that's what we've got here. We're looking at the log magnitude. That's a typical way of looking at the data during curve fitting. I can go up here and press the Bodie. Now, a Bodie is typically log magnitude and phase versus log frequency. For curve fitting, we normally leave it on a linear frequency scale so that we can separate the resonances a little more clearly. But here I'm just scrolling through, and you can see this is the experimental data. So let's go back into curve fitting. Now I have something called a quick fit, so we're not going to spend much time on curve fitting here today, but let's just go through and press this button called a quick fit. You can say that bingo, it quickly curve fit all my data, and the red line is the analytical FRF function laid on top of the experimental data. Now you can see there's some differences here. The phase is wrapping around between minus and plus 180 degrees, but where the curve fit is most concerned to me is in the vicinity of each resonance peak. Not only does the red line lie on the data in the vicinity of the peak, but the phase is important here. So you can see the negative going phase in the vicinity of each of the resonance peaks. So a good curve fit is when I match up between the fit function and the data in the vicinity of each resonance peak. Down here is a mode indicator. This helps the curve fitter decide how many modes are in the data. You can see that it's got 10 modes picked out, and then it's gone through and done the curve fitting and filled up my spreadsheet over here with modal parameters. Frequency and damping are quite different from one mode to the next. The damping varies. Some modes are more heavily damped than others. And then the residues over here, let's just drag them over. I can drag this, here, I'll make this a little larger, and then we'll drag the the residue. Well, this is the method. Let's just drag the residue over here next to the damping. Let's put the damping over here next to it in percent. Residue, magnitude. Let's see, where's the phase? Phase. So we're going to drag that over here too. So those are the important parameters. And there's some other parameters in the spreadsheet here that are not as important to me right now. So I've got frequency damping in two different ways. Percent of critical, which is just a ratio of the damping in hertz divided by the frequency in hertz. That's an approximate value. And then the magnitude of each resonance and its phase. So those are the modal parameters that were used to build this fit function here, what we call a fit function, the red line laying on the data. Okay, I'm going to go ahead and save this data. So let's save that into what we're going to call our EMA mode shapes, and we'll replace it. Okay, well let's get out of this, and I'm going to put it down here for a minute. And here's our EMA mode shapes. Let's make this large so we can look at them, because this is a modal model. So what I mean by modal model, you can say this is called a residue mode shape, and here are the DOFs. They match up 1-for-1 with the FRF data. I've got 99 components in the mode shapes. The magnitude and phase are the residues down here, and then the frequency and damping are in this spreadsheet up above. Now, this is a modal model because my FRFs have been scaled properly. And what I mean by that is that we put in the right sensitivity for the sensors, the load cell and the accelerometer, when we took the data. Now, that's not always possible. Or in some cases, if we're just doing quick and dirty, we want to look at mode shapes. We don't need to scale things. But if we're going to use SDM to predict physical changes, we need what we call a modal model. Now, one of the problems with this modal model is that it is only going to work between the 15Z reference and then each of the roving degrees of freedom. So if I go into SDM and use this data as my unmodified structure, the only modifications I can make are between the roving and the reference, 15Z in one of these rovings, because that's the information that I have in this model here. What I'm going to do with this model, though, is I'm going to rescale these mode shapes down here under scaling. So I've gone into tools, scaling, residues to unit modal mass shapes. Now this is going to do a number of things to my data. Let's just go ahead and do it. Now it's done the scaling. It says, where do you want to put this data? Let's just replace the residues with the unit modal mass mode shapes. Now, in order to do this rescaling, let me stop this for a minute. We had to have a driving point. And the driving point is when the roving and the reference accelerometer locations, in this case of the sensor, the hammer, and the accelerometer, are the same. So right here is my driving point, 15Z and minus 15Z. So measurement 45 is a driving point set of data. And these are the residues over here with some small phases in them. That came out of the curve fitting. And you can see the units are G's per pound second. It's got units in it because this data has been scaled properly from the FRS themselves. Now when I go in and do the rescaling to unit modal mass, residues to unit modal mass shapes, and I'm going to replace these with the, now you can see I've got unit modal mass mode shapes. My units are now inches per pound second. So the data has been integrated and I've gotten rid of the reference. So these mode shapes now can be used in SDM to do modifications between any 2 degrees of freedom in the mode shape and or at any of the degrees of freedom. We're going to add some springs to the Jim beam between the top and bottom plate. This modal model can now be used to do that. Now, how do I know whether these mode shapes are accurate? Well, one of the ways we can check that is to synthesize the FRFs that these mode shapes will create if I go ahead and do FRF synthesis, and then overlay them with the original data to see whether, in fact, this modal model matches up with the experimental data that I measured in the first place. So let's go ahead and do that. I'm going to take Tools, Synthesize FRFs. It's another command now. I'm right-clicking in the shape table. I'm going to use this data, and you can see because I have unit modal mass shapes, I'm going to scroll down here, hold down so my roving DOFs, I'm going to select all 99 of them, and then over here for a reference, I'm going to select 15Z, because that was my original data that I took. The FRF data was from a reference of 15Z where it was impacted, and number of samples up here doesn't really matter, because when I paste this data together, MeScope will interpolate between samples so that I can match up apples and oranges, so to speak. So I don't need to really worry about that. Let's go ahead and synthesize. Now I want, again, because this data is in displacement units, inches per pound second, I want to compare it with my original FRF data, which was G's per pound. So I'm going to have it double differentiate, and actually it will do it on the mode shape data itself. MeScope will take care of all that. And now it says, where do you want to save these FRFs? I'm going to put them into a data block called synthesized, and we already had that. So here it is. Here's my synthesized FRF data that was built from this modal model. Now I got to do a couple of things here. First of all, my reference was minus 15Z, so I'm going to double click on the DOFs column, and I'm going to change. I'm going to do an add to, and I want to add a reference of minus 15Z to my DOFs, and I want to leave the roving alone but change the reference. So I'm going to go ahead and add a minus 15Z to my DOFs. Now you can see I've got the same DOFs as my original measurements. The other thing I need to do, you can see it's because my unit modal mass shapes were inches per second, or inches per pound second. Now I've got FRFs in inches per second squared. Those are acceleration units, but they're not in G's. So I'm just going here and tell it I want G's per pound. And I'm going to change all of the units. Now it says, do you want to rescale? And I'm going to say yes, because I'm changing units. And now I got a new set of FRFs that are G's per pound, and I've got the correct degrees of freedom here. Now I ought to be able to compare these with my original measurements. So let's go back and see if we can find the original measurements. I've got the synthesized. I don't have them. Let's get the original FRFs. Okay, we still got the curve fit function. I'm going to go in and zero that out because we don't need that anymore. And now we'll come out of curve fitting. So here's my my original data with the correct FRFs, correct units, correct degrees of freedom. I'm going to now paste my synthesized data in with the original measurements. And now I want to do something in order to compare things. I'm going to, down here, format overlay by DOF. And there it is. So now you can see that I got a little problem here. I got the phase doesn't appear to be overlaid correctly. It looks like I'm out of phase by 180 degrees. So how can I fix that? Now, I thought I had done that, but let's go back. And I'm going to undo this paste here. So we'll get our original FRF measurements back. These are the original. Okay, you can see a little bit of noise on there, and there's actually evidence of out-of-band modes. You can see the steep ramp here. This is an issue with curve fitting, always to deal with the out-of-band. Let's go back and take our synthesized data. I'm going to make it large here. And okay, we're all unselected. I'm going to multiply. I thought I had done this. Oh, maybe I didn't do it. That was the thing I needed to do. Math, scale. I'm going to scale all this data by a -1. Now, if I click down here, it says 1 with 180 degrees. And where do you want to save it? I'm going to replace it. So now I've multiplied all my data by a -1. See, I changed the DOF here, but the data was synthesized with a +15Z. Now it should be correct for the -15Z. Let's go back and get our data block of measurements and paste in the measurements, the synthesized measurements. So we're going to paste them in, and now we're going to do an overlay by DOF. There we go. So now you can see the magnitude and the phase. Again, this is synthesized data overlaid on the original data. Let's go down here to the driving point and just see how well things match up, because we used a driving point. Oh, it's in here somewhere. There we go. So there it is. You can see a pretty good match, magnitude and phase of the synthesized and the original measurement. So that's one way to validate the model, the modal model. We can go ahead and use this modal model now and do some SDM, or we could go ahead and, let's say we didn't measure the driving point and we just had some residues, or we had some OMA data where we couldn't measure the forces. We couldn't measure all we had was a curve fit of some cross spectrum or ODS FRF data. We couldn't measure a driving point. Another way to scale the data is to use FEA mode shapes. So let me do that. I'm going to go into my FEA model now, and let's just go and up here under FEA, I'm going to calculate FEA modes. Okay, this model already has 80 FEA quads. So those quad plate elements, or wherever there was a quad surface, I can go into my FEA assistant and add a quad element. Well, let's just take a quick look at this. So we're doing a lot of different things here, but I'm going to go up here under FEA quads, and here in the spreadsheet I can see here are all the quads, and they're all using a property called plate 1. So I can go in there and look at that property called plate 1. Plates, here it is right here. It's an aluminum plate, 3/8 of an inch thick. So that is what we're using to model the aluminum plates of the gym beam. Okay, well, let's just go in and calculate. We've got this model all set up. We've got to go up here and calculate the FEA modes. Yes. I'll say okay. Let's store those into their own shape table. And here they are. Okay, it says we're going to go ahead and assign them. They've been assigned. So if I start the animation here, let's put these over. I'm going to arrange for animation, so they're over here on this side. And let me close some of these things so we can look at the FEA shapes. Arrange for animation. Oh, wrong model. We'll put him down. And we'll put him down. And now we have a FEA model. And we should be able to start the animation and look at these shapes. So we're not going to spend a lot of time on this, but you can see the solver has given me some rigid body modes and then a bending mode of the back plate and then a torsion mode. Now we haven't looked at the experimental data, so let's go ahead and do that. And the first way to compare the FEA and the experimental is with a MAC calculation. So let's display the modal assurance criterion between our FEA shapes and our experimental mode shapes. This is saying, do you want to unselect? I have something selected here from animation. I'll say no. And let's compare them with the EMA shapes. And here's a MAC plot. Let me make this larger. And you can see a pretty good correlation here between shape number 8 and experimental EMA shape number 1. The frequencies are quite different, but the shapes match up pretty well. Anything over 90%. Now out here we got down to 82%, 85%. Those are marginal, the last couple of shapes here. But I can go ahead and let's just arrange things here a little bit, and let's get up to EMA shape. So we're going to, again, this is validating our models. We have a FEA shape, and it looks like we've got a pretty good correlation between those shapes there and the EMA shapes down here. That's pretty good correlation. So what we could do, and let's just say we didn't have UMM shapes down here, we just had some OMA shapes or some unscaled mode shapes. We didn't properly scale our FRFs and so forth. We can use these EMA, the FEA shapes, to scale the EMA. So how do we do that? Well, I'm going to come down here to my EMA shapes, and there's another command in here, scaling, and down here, let's put this up so we can see it a little better. There's a command in here called scaling, tools, scaling, unscaled to scaled shapes. So again, this is a way to take our experimental data, which may not be a good modal model, and we can scale it using the FEA shapes that have been scaled to unit modal mass. Now, I have to take that on faith. That's what our solver does, because it has the mass matrix for the model, so it scales the mode shapes to unit modal mass. So I'm going to use those mode shapes here to scale. Okay, it says, now do you want to unselect? Now this scaling is a 1-for-1. Each FEA shape, which I've already seen matches up pretty well with my EMA data, that's a mode shape match. The MAC will just match the shapes, not the scaling. I'm going to say no, I don't want to unselect. And these I can save now into modified, let's just call it, well, these are modified let's create a new one, and we'll call it rescaled EMA shapes. So there's the rescaled, and we'll say OK. So now I have a modal model that is pretty much the same, but it's been scaled. Here's my other modal model, my EMA shapes that were scaled by using a driving point residue. You can see here, let's just compare a number. This one says 4.19, this one says 4.32. So they're a little bit different in value. But if I look at these scaled shapes and I compare their MAC values with the FEA, no, they still match up quite well. Let's compare them with MAC value with my original unit modal mass EMA shapes. Okay, they match up very well. So what this is saying is that the scaling, the rescaled EMA shapes match up almost perfectly with the scaled, the original EMA shapes. So the scaling just, again, this would tell me that if I didn't have EMA shapes that were properly scaled, they were from OMA or they were from, I didn't measure a driving point, I could use this FEA model to scale them properly. And now I have a good modal model. So let's go on. And what I'm going to do here, I've got some hotkeys up here. And I'm going to just push these hotkeys and we'll look at using the EMA shapes as our modal model, or we could use the rescaled, won't matter. They're both unit modal mass modal models now, but let's just go ahead because I think that, now what's going on here is that I pressed a hotkey, and a hotkey of course runs a macro, and this macro is saying we're going to add, SDM will calculate new modes when a spring stiffener is added between the top and bottom plates. Let me stop this, and I'm going to hold down the control key, and that will show us, here is the script that the macro just ran. So you can see it's doing a bunch of different things. It's setting up the springs, but right down here, let me see, where is it? I don't see the SDM calculation. It's positioning. Anyway, let's just go back and modify modes. We're selecting certain, okay, we're getting all the modes out of the, this is our modified modes. EMA shapes, we're unselecting, user dialog, new modes. Okay, so we have another script called new modes, and we're going to run that script once. Let's go look at that real quick and see what that looks like. That's where SDM is actually going to be called, and it's going to do calculate new modes, color Jim beam, calculate new modes, and then it's doing some other arrangement with the windows here. So let's go back and push this button again. This is all set up to automatically do everything. I'm going to say OK. And there we have, let's see if we can turn off point labels. OK. So on the left, we have the model with the spring attached. On the right, we have the unmodified. And then over here, I've set all this up so that, let me just rearrange here. We've got, and let me change this to show, we'll look at this in a minute, but here are the modified modes up here. Down below here are the original EMA modes. So this is the original model, the unmodified. Up here is the new modal model. So you can see that spring, the first mode. Oh, and the other things that's turned on here is to compare mode shapes with the maximum MAC value. Where is that? That's in the animate menu here. If I go under compare, you can see I've got maximum turned on, and then this, we're flipping signs here so that things will match up. You can see that the shapes don't match up, so I got another hotkey that flips the sign. Okay, and that just ran its little script, and now they match up. So as I click down through the modified modes, it's going to display the unmodified that matches up the closest with the modified based on their MAC values. So you can see the first two modes weren't affected by that spring. Those are the first two modes of the beam. There, the third mode, you can see the modified structure has a brand new mode in it, and that mode is reflecting the presence of the spring. And the closest one to it was one down here at 461 that of the unmodified, and it only has a correlation of MAC value of 60%. So that's as close as the match could come. Here's 492. That mode was not affected by the spring. Neither was this mode. So you can see putting that single spring on there. Now here's a brand new mode, 862. That's a new mode, and it really doesn't correlate very well with any of the unmodified structure modes. And we go on back down here. There's a mode that was not affected by the spring. And there's another mode that was not very much affected by the spring. And then finally, another mode, not affected. It's 100% MAC value between the modified and unmodified. You know, even though there's a little bit of phase. This last mode is what we call computational mode. So you can see from the mode shape that the modal model, that mode there was kind of making up for the fact that our modal model only had 10 modes in it. We had 10 modes. We didn't have all the rigid body modes. We didn't even have the first bending mode. This mode up here is a torsion mode of the back plate. So the first bending of the plate, the back plate that showed up in our FEA model, is not even included in this EMA model. So we may want to go back and add that shape in from the FEA. We could add it from the FEA, add it in with our EMA shapes just to have a more accurate modal model for the structure. Anyway, so that is SDM. We ran SDM by pressing this hotkey. Once I have the hotkeys set up, I can press them at any time. But let's go look at something else that I want to show you, and it's called Modal Sensitivity. So I'm going to stop this, and let's go look at the spring. You can see that the script that this hotkey ran, it hid 3 other springs. The only spring that's visible is the spring number 1, which we can see over here on the model. Now the way SDM works, I can put all these other springs on my model, and I'll run those in a second. Well, let's just go ahead and do that. I'm going to press this second button here, which says 2 springs. So we can run these scripts as many times as we want. Now I have 2 springs. SDM will calculate new modes when 2 spring stiffeners are added between the top and bottom plates. You can see that there's still 2 more springs here that are invisible, but now I've got 2 visible springs. Their property is called spring 1. We'll go back and look at that in a minute. Let's just go ahead and see what this does. Okay, so now I got another set of modified modes over here. 165, it's matching up pretty well, 100% with the unmodified 164. Frequency is almost the same. There's another, so those first 2 modes are still there. The second spring didn't do anything to remove them. There's a third mode. It it used to be the fifth mode. So two of the modes in the unmodified structure have been eliminated by that second spring. And there's a mode that's still around. Those two springs didn't change anything. There's a brand new mode. See, it doesn't correlate well with anything of the unmodified structure. But you can see it's clearly showing the effects of the second spring, of both springs. There's a new mode. Doesn't really exist in the unmodified structure. There's a mode that those two springs 100% correlated with one of the unmodified modes. That one wasn't affected. And there's that high frequency there. Now we've got two computational modes because of the two springs, or let's just say the severity of the modification. I get two modes in there that shift way out higher in frequency beyond the highest of our original unmodifieds, which was the 1500 hertz here. See, I can click on either one of these tables and now it's finding the one that matches up among the modified the best with the unmodified. There's no match there, and I can walk through the unmodified to see which ones match up the best among the modified. Okay, let's go back to the first case because I want to show you. We're going to just run this case again. This is with the single spring, and now I want to stop this, and we're going to look at something called modal sensitivity. Now, if we go up here in the SDM menu, calculate new modes, that was being called from the scripting when I press the hotkey, and but the second command in there is called modal sensitivity. So let's execute that and see what that's all about. I think I mentioned in the introduction what this is asking the question, okay, I have a spring. I want to put a spring between top and bottom plates, but I have no idea how much stiffness I should put in there. But I do have an idea from our modified data here what the frequencies of the modified structure are. So here I'm going to simply ask if I have a third mode here of 442 hertz, how much stiffness will it take to create that mode? Down here, see, there was no mode at 442. They went from 164, 224, 347, and it jumped all the way to 460. So those unmodified modes, there was no mode at 442. All right, SDM sensitivity is saying you've got one spring visible, hide all the other ones. Okay, they're all hidden. The mode shape should animate before you can use SDM, because SDM is going to look at the assignment of each of the measurements to the model and use those assignments to do its calculations. So I have to have mode shapes that animate correctly. The advantage there is I can put modifications between unmeasured points. We use interpolation to animate unmeasured points. So their assignments are different. We used to call them animation equations. Now we just call them a measurement assignment. SDM uses those to do its calculations. Okay, so now it's going to say select UMM mode shapes of the unmodified structure. So those are the EMM shapes, or the EMA shapes. Now I have one selected at 99 degrees of freedom. It's going to detect that and say, do you want to unselect? And I will say yes. Okay, this is the sensitivity spreadsheets, and you can see there's two of them here. On the top are the frequencies of the unmodified structure, and then what's called a target frequency and target damping. So if I were adding dampers to the structure, I could specify how much damping I wanted the damper to have in it. Here I'm going to select the third mode, and you can see the unmodified is 347, but I want the modified to be 442, which is what I've already seen over here. So let's put in 442 as a target frequency, and then down here I'm going to select the spring element, and its current value was 1,000,000 pounds per inch. Where'd that come from? That was the spring property of spring 1. If I look over here for spring 1, that property there was 1,000,000 pounds per inch. How do I know that? Well, let's go look at my FEA properties. And here under springs, here's spring 1, 1,000,000 pounds per inch. So I didn't know how much to put in. I just put in 1,000,000 pounds. And that's a pretty stiff spring. A lot of stiffness between top and bottom. Basically, I'd have to push down with 1,000,000 pounds to make it move an inch. So let's go back here and do modal sensitivity and see if we can get away with maybe a little less than that to cause this third mode to go to 442 hertz. Now what this sensitivity is going to do is that SDM is going to run all these cases between 10,000 pounds per inch and 2,000,000 pounds per inch. And it's going to run 500 cases very quickly for me, and it's going to then sort out all the answers that it gets and give me the one that minimizes the difference between the solution frequency and this target frequency of 442. So I'm looking for a solution that will give me a mode at 442 that minimizes the difference here between the solution and my target. So let me go ahead and do that. I'm going to hit the go button up here, solution, calculate, and it's going to say, you're going to give me a warning. You can see I could have a lot of different properties down here that I could be iterating over. SDM, we call this brute force or exhaustive search. It will find the best solution among the 500 that it tries, which minimizes the difference between 440 and whatever the solution is. So let's just go ahead and run that. It's racing through all the calculations, and bingo, it's finished. So it just did 500 calculations, and it came up with an answer of 145. So quite a bit different, 145,000 pounds per inch, as opposed to 1,000,000. And if I look over here in the solution, I got 442 for the third mode, and I got a whole bunch of other frequencies here. So this is my modified set of modes now. SDM, calculate all these. I could go ahead and save these. We can do that, and we can animate them, and we'll see that now we have a mode at 442 by simply applying that amount of stiffness between top and bottom plates. Quite a bit less than I had done. What this is telling me is that this is kind of like a brick wall, and all structures are like this. I can only push that mode so far by adding stiffness, and even if I add 1,000,000 pounds, I can't get it to go past 442. Let's select a few other modes here. So these modes are, I need to put in some targets here, 492 and 634. So let's just put that in. I'm going to put in 492 and 634. So now I'm going to say, give me the best solution that matches up those three frequencies, which I've already seen over here. My 1,000,000 pounds has given me those frequencies in my modified structure. So run this again and tell me how much stiffness I need to make those three match. You can see I can play the what-if game here in a lot of different ways. Okay, so it's running through now, and it's done. Very fast calculation. And you can see that almost the same amount of stiffness, 145, slightly different number, not a whole lot different. And now I have a solution here that's 442, 492, 634, and some change. Let's just try it one more time. I'll unselect everything. Let's go down here to this 9th mode, and let's put in a value there of what was it, 1554. So rather than the 1300, which is what the unmodified had in it, I'm going to put in the 9th mode at 1554, and we'll see how much stiffness it takes to just match that frequency. You can see that 145 almost, well, it did it. So let's just see how all those solutions will stack up here. A little bit more. See, I had to go to 219 pounds per inch, and I got that mode to match up. So this is like squeezing a balloon in the sense that I'm stiffening the structure between top and bottom plates, and here I'm asking, well, how much stiffness does it take to make that 9th mode actually turn out at 1554? You can see the other ones are pretty close, 440, 492, a little bit different answer. I can run as many cases as I want. Now, if I change this to more steps, I will get more resolution between my solutions. If I change it, let's just change it to 100 steps. So that will run very quickly, but I won't get something as close to the 200 as the 500 steps. Now, quite a bit different. 30,000. See, that just gave me quite a bit different answer because I didn't have the resolution. If I put that back to 500, I can go ahead and get the answer back. So now if I save this solution here, you can see this scroll bar over here gives me all the solutions, all 500 of them. So I may not want to implement that one, but you can see as let me make this large here, as I scroll through the solutions, I can pick out any solution that I want here, and you can see they're varying quite a bit in terms of the stiffness. It just shows you how sensitive the structure is to that stiffness between the top and bottom plate. Now I can do this with 2 springs, and I can do it with 4 springs. Same thing. Let's go run the 4-spring case. We didn't run that one yet. Okay, 4 springs. SDM will calculate new modes when 4 spring stiffeners are added between top and bottom plates. So you can see it selected all of them. So they're all going to be used by SDM. And it went ahead and calculated the one on the left is the modified. Now we've gotten rid of that torsion mode completely of the back plate. Well, here it is. This is a higher frequency torsion mode. But the first mode of this structure is the bending mode of the top and bottom plates. SDM got rid of it. There is no, if I go click down here, there's nothing that correlates with this torsion mode of the unmodified structure. So putting all those stiffeners on there got rid of that torsional mode. It's gone. The first mode now is 225. And as I walk through here, you can see that mode was there. That mode also was in the unmodified structure. There's a brand new mode. Doesn't correlate much with anything. There's a new mode. So putting 4 springs on, there's another new mode. I'm looking here at the MAC values. They're very low. It doesn't correlate with anything. There's that mode is still around. Correlates very well, the 1500. But you can see because of this truncated model, I've got 3 computational modes in here now. And I can just tell that by looking at their mode shapes that they are not showing the effects of the spring. But the one at 1500, that correlates well with the unmodified structure. Okay, I am done, Brian. Do we have any questions? I forgot to ask for questions, but do we have a question about anything that I discussed?
No questions so far.
All right. Well, we've spent an hour together, and I wanted to show you the modal modeling and how we set that up, the different ways we can scale our data. And then once we have a good modal model, we can go in and use SDM, use the modal sensitivity to look at how sensitive the structure is to performing these modifications. Fairly simple structure. We could get into more sophisticated modifications, but SDM pretty much works the same way no matter what we give it. Sometimes we can work with just a couple of mode shapes in our modal model if in fact they represent the dominant dynamics of the machine or the structure in the frequency range that we're interested in investigating. Here we went out to 1500 hertz. There are many more modes in this structure beyond 1500. We could add those. We could get them from FEA and use a hybrid model, which would be half experiment, half FEA. There we wouldn't have to take very much data. We could simply take the FEA mode shapes and the EMA frequencies and damping and use that as a hybrid model in SDM. Okay, that's the end of today's session, and we'll look forward to seeing you next month with another 1-hour webinar on the use of MeScope. Thank you for being here.